Hi. Hi. How are you guys? I'm Diabora. So I'm sorry for making this video, and I take so many times, right? So okay, in the previous video, okay, I'm so sorry because I take so much time, and it's because I was busy actually. Okay, so in previous video I simulate this model, and I actually shown you that how this model actually work, right? So then in today's video I want to I have to open the paper. Okay, so here in this paper you can see that, okay, in this video I will discuss about this figure C, okay, figure 2C. So I will discuss how you can draw this figure. It's actually called confinement loss curve, okay, sorry, it's confinement loss curve, and you can call it phase matching curve, okay. So if you can draw this figure, then you can draw figure A of figure 3, okay. So I have to open the Excel file, okay. So okay, for this you can see here that the wavelength range from 900 to 100, how much, 1090 maybe, right? So I have to simulate this model for refractive index 1.42, okay. So in study, click right and take parametric sweep. So in parametric sweep you have to add wavelength, okay, then plus, it means add, then you can add wavelength, which is lambda actually. So lambda. So in my previous video we can remember that we take lambda as L, okay, wavelength as L. So you have to select the name of parameter. So here you can see that our wavelength is defined in L, and initial wavelength was taken 0.65 micrometer, okay. So take L, and then you have to define the parameter value list, okay. So from this range, okay, you can select that a step, then the starting point. So it will be from this figure, you can see that it will be start from 900 to 1090 maybe, okay. So I have to simulate it from 900 nanometer, okay. This in the paper you can see that it is start from 900 nanometer and to 1090, right? Okay, 1090 nanometer, and the step size will be 10. You can take it 1 or 2. So for first simulation I take it 10, okay. So then replace, okay. So, okay, we define the unit and also the range, okay. Then for this we have to calculate the confinement loss for this refractive index 1.42, okay. So we have to define the refractive index 1.42 from the Na, okay. So here you can see that Na is equal to 1.43 is defined, so we have to define 1.42, okay. So now Here you can see that mesh is okay. Now from model analysis we have to search more modes, so because we need some SPP mode and core mode as well. So maybe we can take 8 or 10. 8, okay. Now we have to compute it. So okay, let's compute it. It will work, right? So I think it will work. Okay, so in this part my laptop is little bit slow, so it will take so much time. So in that time you can see my paper that here we use this here we use this model. It's a V-shape SPS PCF-based SPR sensor for I want to tell you that if you want to design a PCF-based SPR sensor, you have to design a unique model, and then you have to understand that what you want to actually do. So in this model I was trying to reduce the production cost of PCB sensor by reducing the amount of gold layer. So so that's why I propose this unique model. You can search that there is no model like that, or there is no model of V-shape. Okay, so so you can see that here we introduce a little bit of gold. So that's why you can say that we use very small amount of gold. That's why it will reduce the cost of gold. Okay. Okay, so then okay, here you can see that. Oh, another thing I want to tell you that here you can see that wavelength sensitivity is 88,000 nanometer per refractive index unit. Amplitude sensitivity is maximum amplitude sensitivity is 3136. Okay, so here you can see that our model's performance is very good compared to the other models in previous work. So you have to design a unique model, and you have to understand what you are actually working, what you are doing actually. So not only you have to design a unique model, but also you have to show the performance more than the previous work. Okay, so here you can see that the conversion plot. Here you can see that the two wavelength is done, two wavelength simulation is done. So it will take so much time. If you want, you can skip this part actually, because it will take so much time for the simulation. Okay, and if you want, you can mail me, okay, for any help. Okay, actually I'm recording my voice after recording the video, so sometimes it's not matching the video with my voice, because in the recording time I don't know how, somehow my voice was not recorded. That's why I'm recording after this video record. Okay, I'm recording my voice after this video. So it's another paper of we have done this work. So here we designed a circular shape, and this shape has very outstanding result. You can see that its wavelength sensitivity is 1005, sorry, 1,557,000 nanometer per refractive index. So it's quite impressive, right? From this, mm, it's also a very good work. Okay, so you can see this work also, and there is another work I have done. It's published in Nanoscale Advantage. It is also a Q1 paper, so Q1 journal, and it's also open access. You can access this journal easily, and so it's another design. So here we introduce double V, okay, for both side. Okay, that's we can get here in in this paper. We design double V shape. That's we can get more sensitivity or more outstanding result. Okay, so this paper is also good. You can see the result here. You can see that the wavelength, its wavelength sensitivity also quite very high. So from this paper you can see that its sensitivity was 88,000, but it's from another, but its sensitivity is 1,43,000 nanometer per refractive index unit. Okay, so another thing is from this paper 3, you can get the optimization process also for PCF-based SPR sensor. Okay, and you can get my paper from searching my name in Google, MD Abu Huraiya. So from Google Scholar you can get it. Also you can get it from ResearchGate. So from ResearchGate you will get this paper. Okay, so okay, I want to suggest you that you can skip this part. Okay, okay. Okay, simulation is almost done, so it will take quite a little bit time. So after the simulation we can explain what we are going to do actually. Just stay tuned. Okay. You can see that my laptop is very slow, and that's why actually I'm uncomfortable. I was uncomfortable to make video. Okay, here you can see that our simulation is done. So now what we have to do actually, simulation is done. Okay, Now we have to find the exact core mode. Okay, the core mode we are actually looking for. So after getting the exact core mode, then we can plot a graph, confinement loss curve. Okay, so from this you have to select study one parametric solution, or the study you are doing actually. So from electric field. Okay, so if you here, it's a very important thing that if you take the which color it is, maybe, okay, maybe something red, right? Okay, so if you take the red color up, then it will change the wavelength, not actually mode. If you take it down, then it will change the mode actually. Okay, so if you take it down, it will change the mode, but not it will not change the wavelength. Okay, so you have to search the exact mode. Okay, so from this we will search from the starting. Okay, so okay, in this paper you can see that the core mode is like this. Maximum light is confining in the core. Okay, so we have to search this thing. Okay, for wavelength 900 nanometer. Okay, so for this maybe okay, just change it and take it down. Thus you can change the mode. Okay, not the wavelength. So I have to search the core mode for wavelength 900, so I have to change the mode. Okay, so I have to take it down. Okay, take it down. Okay, then change the mode. You can see that the wavelength is not changing, just the mode, effective mode is changing. Okay, so I think this is the exact mode we are looking for. So we have to introduce the arrow surface, click right, then you will get the arrow surface. Okay, in this arrow surface you have to take the from present parents. Okay, you have to take it from parents, from dataset, and don't take anything else. Okay, you have to take from parents. Okay, so from here you can change the size of array. Okay, you can change the size of array from here. Okay, if you select this scale, and you can change the size of array, you can reduce the size, you can increase the size. Okay, from surface you can change the color of the PCF. Okay, this is okay for the paper. Okay, to get the paper color, this is exactly the color which color we used in paper. Okay, so okay, I think it's okay, right? Now okay, now you can see that maximum light is passing into the core or center of the PCF, and a little bit light is passing through the along with the plasmonic material or gold layer. Okay, so and arrow direction, you can see that arrow direction is the x direction. So it is x core. Okay, it is actually the x core. So in the paper you can see that we work on only for X core, we don't work on Y core. If you want you can work with both core. So from this for this work we actually work for X core only. We don't see Y core. Okay. 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 It's okay. Then what you have to do, we have to find the loss. Okay, from the effective mode you can from the effective mode you can find the, okay, you can change here. Now you have to change the wavelength. Okay, because we have to search the, okay, from here you have to take the global evaluation and take the expression from here, electromagnetic wave, and from, I think from global. Okay, from global you have to take if EWFT dot NEFF. Okay, effective mode index actually it's, so you have to evaluate it. So for evaluation, for evaluating it, okay, take it down. So we need actually table. Okay, so that's why we are doing this thing. Delete this table, previous table, we have to delete the previous table. Then okay, here you can see that the core mode we are for getting for now we have to change the wavelength. You can see that for 910 nanometer wavelength we got the uh, effective mode at the same point. For the next wavelength we got the effective mode for at the same point, and next. So you can see that the position of effective mode is not changing. Okay, so it's quite good. Okay, if the position of the resonance effective mode change, then it will make some problem. Okay, because not actually performance, it's for taking the data. Okay, taking the data, it will make some complexity. Okay, so from this you have to take a study one parametric solution, because we take the parametric sweep. Okay, okay, from here you have to choose the outer solution, not data only. Okay, so if you choose the data only, then it will create problem. Okay, now you have to evaluate it. Just click evaluate. Okay, it will take some time. Okay, so we got the all effective mode. Okay, we got all effective mode. What happened? Oh, okay, so we're trying to put the table to a suitable position. You can take it here. Okay, don't need to take anywhere. Okay, so you can see that we got all effective mode in this table. Okay, so you can see the position of effective mode is core mode. Okay, is 1 2 3 4 5 at a position of 5. So click here. Okay, so here you can see that all selection is okay. You don't have, you cannot select auto. Okay, okay, then you click right, you have to click right, then copy selection and headers to clipboard. Then you have to open the Excel file, then you have to paste the data here. Just put it, then you will get the all effective modes for all the wavelength. Okay, just copy it, then you have to paste it here. Okay, just right click, then paste special, then you have to transpose it. Okay, click transpose, then okay, then it will be transposed. Okay. Now you can delete it. Okay, just delete it. Okay, so for it is effective mode, effective mode, effective mode for 1.42. okay, for 2 maybe. So I think I write something wrong. So wavelength will start from 900, then it will 910, so is equal to, okay, then drag down. Okay, so I have to calculate confinement loss. Okay, the equation, you have to know the equation of confinement loss from paper. You can get the confinement loss equation where this is alpha. Yeah, alpha is actually confinement loss. Okay, so the equation of confinement loss is 8.686 into K naught, imaginary part of NEFF, into 10 to the power 4. Okay, so I think in the paper I write it wrong actually. Sorry for that. Okay, in the editing time, I think in the editing time I made a mistake here. So it should be imaginary of NEFF. Okay, not imaginary of 3. Okay, it should be imaginary of NEFF only, not 3. So I'm sorry for it. So I have to write the equation. Sorry, is equal to no, is equal to 8 point, what the value was, it's not showing, 8.686. okay, 8.686 into K naught, right? What's the value of K naught? K naught is 2 into 3.1416 divided by, what is lambda maybe, right? So oh, it's not showing. Okay, imaginary of NEFF. Okay, then put imaginary of NEFF. So imaginary, sorry, I'm writing wrong equation. Imaginary, not in real. In the time of recording I was wrong I think. So it is actually wrong. Okay, so I will correct it after some second. Okay, just skip it. This equation is wrong actually. Not, it's actually in real, it will be imaginary. Okay, and another part is okay, just in real will be imaginary only. Okay, okay, I done it here wrong. Okay, in the time of video recording. Okay, just see what I have done. Just write the same thing what I am writing actually here. Okay, mm. A2 into 10 to the power maybe -7, or what was that? I forgot actually. Okay, so I'm trying to open another. From here I think I get some I get the equation Okay, what is the equation? Okay, this is the equation. So here you can see that it has imaginary, so I made this mistake and I can understand what I have to do. So okay, I'll solve it wait a second, just take me some time. Okay, I paste and down. Okay, okay, now it's okay. Okay, I think I understand right now. Okay, it should be 10 to the power minus 7. Okay. Okay. Now, in that time, I can understand what is going on, but I have to look at the real. Actually, it would be imaginary. Okay. Okay. When I will understand it, just look at. Okay. Now I understand it. That I made a mistake here. Okay. Oh, Excel. Okay, I'm sorry. Okay, now it will be okay. Okay, oh, and the in front of 8.686, what the value is 686, it would be a minus. Okay, in front of it. Okay, now it's okay. You can see that now the confinement loss is okay. Again, just plot this graph, insert and plot this graph. Okay, I don't know why this graph is like that, but I don't know why the graph is not coming the same graph. Okay, so I think in the production time I made some mistake, so it's not a fact actually. So for the material selection, I think I have made some mistake, okay, in the material selection. So it's not actually a problem. And okay, I'm trying to see that why is the first peak first why the graph is not the same of the paper. What, I cannot find it because it's happened. I think it's happened for the material selection. Mm, if you put all material properties same as the paper mentioned in the paper, then you will get the exact graph. Okay, so it's not a problem actually. I think I put some value wrong. Okay, that's why it is happening. Okay, it's not actually a problem. Okay. Okay, actually the main peak is in there. Okay, it's the main peak. This is not actually peak, it's a small peak. So we have to take the peak where we get the maximum loss. Okay, and another peak we don't need to focus that peak. Okay, so it's not a problem actually. Okay, so now we have to calculate the real part of the effective mode. Okay, because we have to plot that graph I mentioned before. Okay, so I have to take the im real. Okay, because we have to take the real part. Okay, im real will provide you the real part of the imaginary of actually complex number. Okay, from the complex number it will provide you the real part. Okay, so now I have to add the real part of effective mode also. So just select this. Okay, now click here, double click. Okay, then is secondary axis, choose the secondary axis. Okay, then it will work like that. Okay, now I have to calculate the real part of SPP mode. Okay, so I have to calculate real part of SPP mode. Okay, okay. So actually what will happen, for 1.42 we got the resonance wavelength at the 990, right, nanometer. Okay, so we'll get the resonance wavelength at the 990, and real part of SPP and real part of core mode will match at the wavelength 990. Okay, we'll see that after the plotting. Okay, so now we have to calculate the real part of SPP. Okay, nothing else. So let me see what I'm actually doing. Okay, what I'm showing in paper. Now I have to calculate the I think some of you guys know that I made a mistake at the time of recording, so I can't record the voice at the time of recording, so I'm recording my voice after making the video. So please take it easy, and I'm sorry for that. Okay. And some of guys, you want to collaborate with me. If you want to collaborate with me, you can email me anytime at my email address. I think you know my email address, I mentioned you before, so you can email me. My email address is abusuraya692@gmail.com. Okay, here you can see that the core mode is like that and SP mode is like that. So we have to search this SPP mode. Okay, so then from this SP mode we have to take the real part. So this is core mode, and how you another thing is how you will understand that is the SP mode. Okay, so and to tell you that at the SPP, at the core mode, you can see that maximum light is confining at the core. Okay, and in the SPP mode you will see that the maximum light will confining at the plasmonic material, but no light will appear at the core. Okay, so then you will understand what is core mode. And another thing, you can find the SPP mode at the resonance wavelength. You can see that the real part of core mode and the real part of SPP will be almost similar. Okay, here you can see that. Okay, maximum light is confining at the plasmonic material, but no light is appearing at the core. Okay, so it is the SP mode. Okay, of the core mode. Okay, there is no another SP mode. Okay, so and the thing I tell you that the real part will be almost same, okay, for SP mode and the core mode at the resonance wavelength, not another wavelength, only for the resonance wavelength, okay. At the resonance wavelength, the real part of SPP and the real part of core will be same, almost same. If you take the uh, I take the division for 10, right, 10 nanometer. So if you take 1 nanometer, then it will you will get exact real part and imaginary part for core mode and SP mode, okay. Okay, now this is the SPP, okay, for now, oh, sorry, okay, then I have to search some SP mode for some wavelength, okay. Just see that for all for wavelength on 1000, the SPP is appearing at the first of the okay. In the global evaluation, now you have to select real, so because we need only the real part, okay. So from here, okay, now evaluate it. It will take some time. Evaluating in your computer, maybe it will not take any time because my laptop is slowing, so it is taking time, okay. What happened? Maybe it overlapped to the first table, so you can delete the table. I will delete the table. Maybe I will delete the table, okay. Just see. Okay, the real part is appearing after the, so I delete the table, okay. Then evaluate again. Okay, now take the first effective mode only, real part of effective mode, because you can see that for all wavelength we will get the um, SP mode at the same wavelength, okay. So for 1000 for 1040, 1050, 30, so for all of the wavelength we are going to we are getting that the SP mode at the same position, okay, at the first position actually. So copy selection and header to the clipboard. Now I have to paste it here, paste it, just paste it. Now okay, here I have to tell you that just takes little bit value, okay, from 970 to 1030 or 40, okay. Just here click the transpose zing, then okay, now plot it again, okay. Filter, select data, real SP, okay, hot event, okay. Just delete this figure, delete, plot it again. Event, confinement loss, real part of okay, insert, okay, plot, okay. Just click here, okay, click here, secondary, click here, secondary, then you can get this figure, okay. I think you understand what I have done here. You can see that we get the resonance wavelength is 1000, but it's the real part is mass at almost at the 900, right? And we in the paper we can see that the real part is appearing at the the resonance wavelength was 990 maybe. Okay, so if we take step size 1 nanometer, then you will get the exact value, because we take 10 step size is 10 nanometer. That's why it will create some error, right? It's not a big deal actually. So it's not actually 900, it's 900, 990 plus. Okay, so maybe 992 or 3 maybe. Okay, so it's not a problem actually if you take the if you take the step size 1 nanometer, then you will get the exact value and exact phase meshing curve. Okay, so I take step size 10 nanometer because my my laptop is slowing, so that's why I will suggest you for phase meshing curve you can take the step size 1 nanometer. Okay, then you will get the perfect result. Now this is the phase meshing curve, so I think you got it, the phase meshing curve. So I will suggest you, this is the phase meshing curve. Okay, then I will suggest you to create all of the confinement loss curve from 1.29 to 1.44, then you will get the this confinement loss figure. Okay, okay, so I think this figure you can create okay, if we simulate and get all of this figure. Okay, thank you guys, thank you everyone. Okay, please create this conformance curve, and I think you can do it.